Hello students, this video explains about Zener diode. Zener diode. You might have seen what is PN junction diode. So on the similar basis, Zener diode is also a PN junction diode where doping concentration is more. That is, we have 1 per 10 power 5 atoms. Okay, doping concentration will be 1 atom per 10 power 5 doping concentration. Whereas in PN junction, 1 per 10 power 8. So in this way, when compared to ordinary PN junction, the Zener diode is highly doped. Okay, so while doping highly near the junction, the depletion layer will be having more recombination of electrons and holes, so that the depletion layer will be forming with a very large thickness. Okay, the width will be more there. Okay, now let's discuss more about Zener diode. So working of Zener diode, as I told you, Zener diode will be mainly used in reverse bias. Forward bias, it will be normal to PN junction diode. In reverse bias, it will have two effects here, breakdown effects. They are called as avalanche breakdown and Zener breakdown. So in avalanche breakdown, we can see that electrons will be getting multiplied. Agitation of those electrons will make it vibrate and hit the other. The other will go and hit. Likewise, it will go on multiplying. So if we have this kind of breakdown is called as avalanche breakdown. Whereas Zener breakdown, because of applied voltage across it, the Zener voltage will be making the electrons to move. Okay, so this one will be taken as Zener breakdown, and we can clearly see when the Zener diode is unbiased, we can see how the characteristic curve very near the junction. So the first curve is charge near the junction. This is the depletion region junction, and this side electrons are there, and this side holes are there. Okay, red color indicates holes. So hole concentration is more in P side, and once near the junction it is crossing down because it is combining with electrons, and then it becomes low in N side. Similarly, electrons here will be more, and then near the junction it is crossing down means since it is combining with the holes, it is going down. And then we can see here electric field near the space charge region is like this. Okay, it is going to negative side, and then the voltage you can see in PN junction it is less, and then moving on PN junction it is less. Then near this we have some voltage. So that is about the voltage. This is about unbiased. Unbiasing means externally voltage is not applied. Okay, initially Zener diode will have that. Okay, now let's see the circuit diagram for Zener diode. The Zener diode indicated here, since the doping is more, the depletion width will be thin, and mainly Zener diode will be useful in reverse bias. Forward bias, it will be normal as PN junction diode only, and in this diagram you can see how it is connected. Batteries and all, you are measuring the voltage using this multimeter, which is kept in parallel. And now let's go for types of breakdowns here. Zener breakdown. So in reverse bias, this occurs when the voltage is below 8 volt. Okay, it should be between 2 to 8 volts. So at low voltage itself, electric field will have more intensity, so that the formation of mobile electron hole pair increase the flow of current here. Since the depletion layer is very thin, it will break down, it will cross this thin depletion layer and enter to the other region, opposite region. Okay, so actually the electric field formed because of this will be in the range of 2 into 10 power 7 volt per meter. Okay, then this type of breakdown is called as Zener breakdown, and what we observe is for low voltage itself we have huge current here. Then as I explained you previously, the other one is avalanche breakdown. So you need to just remember it is just a multiplication of agitated or disrupted electrons, which will break the covalent bond of the other. Okay, so this occurs above the voltage 8 volt. So we go for generally Zener breakdown voltage is very important because at less voltage itself it happens. So this only contributes for reverse bias operation of Zener diode. Okay, so only it is called as Zener breakdown. Next, so a picture view, you can see the multiplication factor, how it is happening. In Zener diode, it is because of applied voltage over there. Okay, and because of the thin width of this depletion layer. Okay, and then next, I already told you how the doping will be done. So this is more about width of the doping and who invented this means Dr. Clarence Zener in the year 1937. Dr. Clarence Zener in the year 1937 found this. Okay, the VI characteristics of Zener diode. So PN junction in forward bias, it follows similar way. And then in reverse bias you can see in knee voltage or Zener voltage, after that it will be constant, that is small change in voltage can't be seen, so it tries to stabilize it. Whatever voltage you increase, it doesn't change it, it will stabilize it. And then you can see huge current flow. Because of this nature, we'll be using this as stabilizers also. In stabilizer circuits, Zener diode will be used. Okay, this one you can see how straight it is. Okay, so we have to talk about Zener resistance here. We have two types of resistance, DC or static resistance. The other one is AC or dynamic resistance. DC or static resistance is the ratio of Zener diode voltage to total current at operating point, okay, at a fixed point. So it is mentioned RZ, that is VZ by IZ at particular point in the graph, in the characteristic graph. So AC dynamic resistance means we cut the graph at 2 points and we see the difference here. Del V del I means two values will be taken as difference. Okay, so in words we can write it ratio of voltage difference and current difference. If dynamic resistance is less, then diode will be better as voltage regulator. So now we'll be seeing Zener diode rating. Okay, we have 3 parameters here: minimum Zener current, maximum Zener current, and maximum power of Zener diode P. Minimum Zener current means IZ min. Actually here it should be min, which indicates that it is the minimum current which makes Zener diode remain in breakdown region. Okay, it is the minimum current in which Zener diode remains in breakdown region. Okay, through the current through it and has more than minimum current, more than Imax, the current will be like that. That is reverse bias means negative, no? So it will be taken as minimum. Generally maximum means it goes in forward direction, moves away towards left side. Okay, in the graph if we see it moves away to left side. And now let's go for maximum Zener current. The maximum Zener current relates to power rating PZ max. So it is the ratio between PZ max and VZ Zener voltage. Okay, this parameter gives maximum current Zener can withstand without exceeding its power rating. Okay, this is a parameter which tells to how much extent Zener can withstand without exceeding its power rating. Okay, so the formula for maximum Zener current is IZ max is equal to PZ max by VZ. And now maximum power of Zener diode. So it is defined as PZ is equal to VZ by IZ. That is power dissipation of Zener diode equals to the product of Zener voltage and current, which will be taken as product of Zener voltage and current. Here by mistake it is written, it is VZ into IZ. Okay, VZ into IZ power, no? Okay, now PZ is less than maximum power rating. Zener can be operated in breakdown region without being destroyed. Okay, now let's go for the effect of temperature of diode. Effect of temperature of diode. So temperature coefficient TC, the percentage change in Zener voltage VZ for every centigrade change in temperature is called as TC, temperature coefficient. So temperature coefficient is defined as percentage change in Zener voltage VZ for every degree change in temperature. Okay, that is mathematically we define this temperature coefficient TC is equal to change in Zener voltage VZ by VZ into change in temperature. That is at what instant we go for this means if we increase the temperature, there results change in Zener voltage. Okay, Zener voltage may change. It may be more or less. Based on that, we have the condition here. So this formula gives you a relation between the Zener voltage and the temperature. So if we rearrange this equation, we can find what is VZ. Okay, so see this clearly. What is VZ? VZ means Zener voltage. Now based on this temperature coefficient formula, T0 will be taken as 25 degrees at which Zener voltage is VZ. Okay, Zener voltage is occurred. Okay, next if TC is positive, VZ increases. As TC increases, okay, TC means the temperature coefficient is positive if VZ increases as T1 increases. Temperature increases, Zener voltage will increase for positive temperature coefficient. So this is more VZ is more and then T1 is increasing. So both are increasing, then we have temperature coefficient as positive. If temperature coefficient is negative, then TZ is increasing and T1 is decreasing. VZ is increasing and T1 is decreasing. If this one is negative, if this one is negative, this is increasing, VZ is increasing, T1 is decreasing. Or VZ is decreasing and T1 is increasing. VZ is decreasing, T1 is decreasing. So this is the condition. We have two cases here. Temperature coefficient is positive, temperature coefficient is negative. And now if we rearrange the formula, we have, actually this should be VZ actually. VZ, no delta here. Only VZ is equal to what? Delta VZ into TC into T1 minus T0, temperature difference, divided by 100. Okay, so if we rearrange that formula, we have VZ is equal to delta T is change in temperature. So finally we have rearranging and all simplifying, delta Vz is equal to Tc into T1 minus T2 T0 Tc into delta T. Simplifying the equation, we have this. Okay, and now what is the condition means, if Vz is below 6, then temperature coefficient is negative, so Vz decrease as temperature increase. Next, Vz is greater than 6, sorry, Vz is greater than 6, temperature coefficient will be positive, so Vz decrease as temperature decrease. So this is the thing. Now let's see the advantages. Advantages means controllability. As we in the reverse bias, as we go on increase the reverse voltage, it doesn't go, it gets stabilized. That is the controllability. So only we can use in stabilizers and all. And size and expenses. Zener diode is very small and it is used in many cases in many electronic circuits and all. Even in cell phones also it is used. Even you can see that in your stabilizers and all. For refrigerator you will be using stabilizers, for AC you will be using stabilizers. So that is the best application of Zener diode. And performance, it is having very high performance standards, and often it will be used in maximum efficiency places. Okay, it will be having more efficiency. And now let's go for applications. Zener diode will be used as voltage regulator. We already discussed about that. Okay, because of the graph in reverse bias, you can see like this it comes. Okay, and then because of that you just go through all those, how the regulator will be used, I minimum and all will be discussed here. We have the power rating here, which already I mentioned, and then the resistance for that will be, for voltage regulator, how the resistance should be means it is calculated using this formula. Just go through that, where IL is the load current, which will be taken as load voltage by load resistance. Okay, what do you mean by load means if the output is connected to a particular device, then it is called as load. Now let's go for next one, Zener diode as a voltage reference. Similar, based on the characteristics of Zener diode in reverse bias, it is used as voltage reference here. The circuit for it is this. Okay, and then factors determining the stability. We have three factors determining the stability of Zener diode. First one, the input unregulated DC voltage Vn, then load current IL, then temperature. So hence the output voltage of power supply can be expressed as, you can have the formula here. So output voltage V0 can be written in terms of dou V0 by dou Vi, output voltage by input voltage into the change in input voltage, plus dou V0, output voltage difference by the load current dou L, plus the change in load current, plus load output voltage change by the temperature here, plus change in temperature. Okay, change in temperature, we write that way. And now we have the coefficients here. Input regulator factor, it is indicated as SV. The first term is taken here, the first term V0 by Vi. Okay, multiplied into where del L is constant, del IL is constant. Okay, load current is constant and temperature is constant here. And then the output resistance R0 is V0 by IL. L means at load only, output side. Okay, so IL is nothing but high output, current at output, where input voltage is taken as constant, will be equal to 0. Okay, and then we have the next parameter, temperature coefficient. Temperature coefficient, it is ST, where it is indicated as V0 by del T, where Vn is made constant and load current is 0. So using this formula, we can have factors indicating the stability. So smaller values of these three coefficients, better regulation for power supply. This is very important. Smaller values of these three coefficients, the better regulation of power supply. The line regulation is defined as the change in output voltage for a change in line supply voltage, keeping the load current and temperature constant. This is called as a line regulation. So we can see the formula here. Formula is line regulation will be equal to change in output voltage divided by change in input voltage, that is del V0 by del Vn. Change in output voltage divided by change in input voltage. Now load regulation means it is defined as the difference between no load voltage minus full load divided by no load into 100, or otherwise it can be defined as no load voltage minus full load by full load. That is, what do you mean by load? Load means if we have any circuit like this, supply voltage here and then resistance, for example you can take PN junction diode itself. So PN junction diode, we have the diode here, and then here supply is given, and then at output side we should connect something else. If I connect LED here, LED bulb here, in forward bias LED bulb will glow. So LED bulb is taken as load for me now. In reverse bias LED bulb doesn't glow. Okay, so that is the intention here. Load regulation means if LED bulb is connected, then it is full load. If LED bulb is not connected, you can observe my hand, circuit power supply here, positive, negative, PN junction diode. Okay, so PN junction diode like this, positive, negative supply, and then here diode connected, and at the output side the LED is connected, one LED is connected. So the circuit is closed now. In this way, connected to diode and then connected to LED, circuit is closed. Okay, so this indicates if LED is connected here, then it is called as load. LED is connected here, it is called as load. If LED is not connected, then it is no load. Okay, I am showing the circuit again. This is the supply positive, and then diode here, PN junction diode, and then here comes, this is just an example to indicate what is load. LED connected, and then the circuit is closed. Supply diode, and then here you have LED, and then you have the supply here. Okay, now going for the next one. Other application is clamping. It will fix the voltage. This experiment you have done in the lab, so you can see how the clamping is done. To particular reference voltage, whatever voltage across this it comes, that voltage is clamped. It will fix that voltage only. Remaining and all, it is clipped off. So only this is called as clamping. Okay, we'll put reference voltage for particular Zener diode. Let that be 5 volt. So below that 5 volt, it will be clipped. Okay, and above 5 volt, output can be seen. So only we have the graph like this. Okay, that is about the voltage clamper. And let's discuss some problems on a Zener diode. So the first one, design Zener diode shunt voltage regulator with the following specifications. V0 is 10, Vin is 20, 20 to 30 variations, and current is 30 to 50 milliamp, and I2 is 20 to 40 milliamp. So we need to design Zener shunt voltage regulator. Okay, so for this, write down the given parameters here. The given parameters written. So we know the formula for power. Power will be equal to voltage into current here. More for maximum values. Maximum values means the second values we take the second values, highest values. So we have voltage and current multiplied here. So voltage is 10. We take V out as 10 here, and load current is 40. I2 is 40 here. So we have 0.4 watt. Hence we have 0.5 Z. 0.5 Z Zener. 0.5 Z Zener means it is the number given for Zener diode actually. Don't worry. It is the number given for Zener. 0.5 WZ1. 0.5 WZ1. Zener can be selected here because of this wattage. That Zener can be selected here. And the value for load resistance RL. So we know the formula here. V0 by IL max. Take the maximum value. We have 200 here. VL for max. So we take min here. Minimum value is taken. We have this. By IL is minimum. If current is minimum, resistance is more. If current is more, resistance is less. So in that way we indicate the parameter here. Don't get tensed. It is inversely proportional to resistance. Current is inversely proportional to resistance. Okay. So accordingly we have this formula, and then value of input resistance R max is equal to, so change in input resistance, change in input voltage minus output voltage divided by load current plus I1 plus I2 maximum. So both the values are taken and substituted. We have 286 ohms. This is the input resistance. Input resistance means near the supply we have input resistance, at the load we have output resistance. If this is the circuit, here we have input resistance, and this side we have load resistance. This current will be taken as load current, and this side it will be taken as input current. Okay. Similarly, if you measure the voltage here, it is input voltage, and this side output voltage. So you can just go through these. I'll send the description. Okay. Now the next problem, second problem, 24 volt 600 milliwatt Zener diode is used for providing 24 volt stabilized supply to a variable load. If input voltage is 32 volt, calculate the value of series resistance required. And second point, diode current when the load is 1200 ohms. Okay, write down the given parameters here. Given parameters, V0 equal to 24 volt, Vi equal to 32 volt, input voltage, power is given as 600 milliwatt, and then resistance this much. So the formula is load current formula, IL equal to V0 by RL, 24 by 1200. So we have 20 milliamp. Similarly, maximum Zener current IZ max is PZ by V0. Okay, so substitute the values and simplify it. We have 25 milliamp. and R max is equal to V naught minus VI minus V naught divided by IL min minus IL max. Okay, so again you can take the values here and then see, substituting the values, we have 8 by 45 into 10 power minus 3, then 16,000 by 9. So finally 177.78 ohm. So refer more problems in the given notes, okay, given textbook. Thank you.